Okay, so first I have to make sure I open it. That's chapter 10, okay. So as I said, today we are covering 6 exercises that are related to chapter 10, and here what I'm sharing with you are already answers. So questions as usual, it's the usual format, and I actually posted this PDF already while you were doing the exam. So uh, first couple of pages or first page are questions and then answers, and these answers repeat question in full, so that way I can cover them right now. So first one, which base is capable of deprotonating one pentyne? So we covered that actually already in chapter 5, and we are repeating that now. Terminal alkynes are alkynes that have triple bond at the end of the chain, which means that they have sp hybridized carbon that is bonded to hydrogen. That carbon-hydrogen bond, sp carbon-hydrogen bond, is slightly acidic. And so terminal alkynes are acidic, slightly acidic. They are weak acids. To deprotonate them, we need very strong base, exceptionally strong base. And so really question would be which of these four is an exceptionally strong base. Now, methoxide is strong but not strong enough, and same goes for potassium hydroxide. Neither of them is strong enough to deprotonate one pentyne to a significant extent. Sodium in ammonia is actually a reducing agent. That reduces triple bonds to double bonds. That's dissolving metal reduction. That's not a base at all. That's actually reducing agent. So sodium amide is strong base. Sodium amide is a very strong base, and that one can deprotonate terminal alkyne, and then product is acetylide. Acetylide is general name. It's an ion that is obtained from acetylene. That would be 2-carbon, so simplest 2-carbon alkyne, simplest alkyne. But also name acetylide is used for any anion that is generated from an alkyne. And that's the case here in question number 2. This is acetylide ion that is generated from propyne. So which of the following reacts with acetylide ion? Acetylide ion, as you can see, is a nucleophile. It has free electron pair. So then question is, which of the following is an electrophile? Which has an empty orbital? And A is not. That one is actually also a nucleophile. Same C. Amines are nucleophiles. They have free electron pairs. Ethers are also weak nucleophiles, but nonetheless nucleophiles. So oxygen, nitrogen atoms with their free electron pairs, they are nucleophiles. This is the only electrophile. And this electrophile is a little bit hidden or masked electrophile because it doesn't have an obvious empty orbital. Instead, it has polar carbon-halogen bond. If carbon-halogen bond is carbon-chlorine, carbon-bromine, or carbon-iodine bond, it's highly polarized towards, it's relatively weak. Carbon-fluorine is actually the most polarized, but it's strong, so that one cannot be broken in reactions like this. But bond to chlorine, bromine, or iodine is both polar and can be easily broken. And that means that carbon effectively acts as an electrophile, because since iodine can leave easily, that leaves an empty orbital here. In this case, actually, assistance from this free electron pair is necessary to push out the iodine. And so B is an electrophile, and that's the product. Now, when you study chapter 10, you can simply memorize this. This is at the beginning of the chapter 10, and you can memorize that compounds with leaving group on carbon, and those are generally alkyl halides, react with acetylides to form carbon-carbon bonds. That halogen is replaced by this carbon nucleophile. When we cover chapter 12, this is actually going to make much more sense, because then you will see the reaction mechanism, and that's actually in part why chapters 10 and 12 are on the same test, because you may think alkenes and alkynes are pretty similar, and they are, and the chemistry of alkynes in general is actually extension of chemistry of alkenes. So triple bond reacts very similarly to double bond. But there are some differences, And also there are some aspects of chemistry of alkynes that are unique to alkynes. And that's why I separate them later, to cover them later in the course or on a separate exam. So correct answer is B. The answers. And for the first one also, the correct answer is B. Okay, question number 3 is a bit different in nature, so let me see if there are any questions. Okay, I don't see any questions. As usual, if you have any questions, type them up or unmute yourself and ask a question. Question number 3. What was the starting material of the following reaction? So in cases like this, you have to work reaction backwards. So reaction is ozonization. Ozone cleaves multiple bonds, carbon-carbon double and carbon-carbon triple bonds. And what is the product depends on the workup, on the second step. Ozone, that will cleave the bond. So if it's double bond, it will cut it and a bond will be cleaved, so completely broken. Both bonds, sigma and pi, are broken. And then second step workup, that depends what we get as products. In case of alkenes, this workup could be reductive or oxidative workup. And then depending on what are the reagents, products could be alcohols, carbonyl compounds, aldehydes and ketones, or carboxylic acids. That could have been on exam today, and in fact it may have been. When workup is just water, just add water at the end, that means that the starting material was an alkyne. Because if alkene is starting material, we have to apply either reductive or oxidative workup. So reagents such as sodium borohydride, dimethyl sulfide, zinc inacetic acid, or hydrogen peroxide. But in this case, when we simply add water, that means starting material was an alkyne, triple bond. And product is carboxylic acid. So starting material had carbon-carbon triple bond, and two carbons that are now carboxylic acids used to be connected, bonded to each other with a triple bond. So what you do is you redraw these two fragments. So this is left fragment, let's say draw it on the bottom. So this carbon is part of a triple bond. You draw a triple bond, and then this carbon is the other end of the triple bond. That's this carbon, and then you redraw the rest of the molecule. Obviously, on the test, something like this would be multiple choice because you're not able to do drawings like these on canvas, or you may have to type up. Then it would be simple compound that you would simply type up as condensed formula as a line of text. So this is the starting material. Again, let me see if there are any questions. Okay, no questions. Let's go back. Question number 4. Provide UPAC name of the product of the following sequence of reactions. So this is one where you use pen and paper, and always write down things on paper. We don't want to just try kind of mentally to figure out what's the product and then try to name it. There are too many possibilities to make a mistake. Just use pen and paper. So there are two steps. First, hydrogenation with palladium in pyridine. This palladium on carbon, that simply means that carbon is catalyst support. Palladium is very expensive, and the reaction occurs only at the surface of the catalyst. So for that reason, for something very expensive, we want to have that catalyst in thin layer on some inert support, something that does not participate in reaction, so that very little of this expensive metal we need to use. And so such inert support is carbon. So we simply spread carbon in a very thin layer on, spread palladium in a very thin layer on carbon, and that's the catalyst. Now, pyridine actually participates in a reaction. It modifies the reactivity of the carbon. So what pyridine does is it's actually catalytic poison. In industry, poisoning of a catalyst is undesired phenomenon. That means then catalyst doesn't work very well or doesn't work at all. But in this case, it's desired property, and the catalyst has specifically been designed to be poisoned, to be less reactive. And this particular catalyst, palladium with pyridine, is a Lindlar catalyst. So, since it's less reactive, then catalytic hydrogenation works in such a way that only more reactive triple bonds are reduced to double bonds, but double bonds are not affected. So palladium alone, if it was just hydrogen with palladium on the carbon, this triple bond would have been reduced to single bond. But because it's palladium with pyridine, pyridine prevents palladium acting as a catalyst to reduce double bonds. So reaction stops with a double bond. And that double bond is cis double bond. Because reaction is syn, addition is syn. Both hydrogens add from the same side, and if they add from the same side, then that means the product must be cis. Alkene must be cis. So that's one way to make cis alkenes. Now, in this case, actually doesn't matter, because this alkene, so that's a product of the first step, this alkene in the second step undergoes chlorination. This is simple chlorination of an alkene. So chlorine adds across the double bond, and we end up with this product. That's reaction product, and now all you need to do is name it. And name is 2,3-dichloro-4,4-dimethylhexane. See, actually, I'm wondering if the alternative name 3,4-dichloro. Let's see. That's interesting. No, that's correct. Okay. Okay. So you see. So name is 2,3-dichloro-4,4-dimethylhexane. This is a little bit unusual that we have, in this case, we have a tie going both from left to right, naming it from left to right or right to left. Because if we were to name this compound from left to right, it's 1, 2, this is 3, 3, 4, 5. So 4, 5 dimethyl, 4, 5 dichloro, 3, 3 dimethyl. Actually, 4, 5, that's 9, and 6, 15. No, actually, that's a larger set of numbers. 4 and 5 are 9, and 3, 3, that's total of 6, that's 15. That's larger sum, larger set of numbers. 2 and 3 are 5, and 4 and 4, 8, that's 13. That's smaller set of numbers, so that's correct. Yeah. Okay, for a moment, I thought that I may have made a mistake. So, simple naming of alkyl halides. Let me see if there are any questions about that one. No questions. Question number 5. What are the products of reaction sequences A and B? So, first sequence A, that's a reaction with dicyamylborane in tetrahydrofurane as a solvent, followed by peroxide oxidation. So, this is variation of hydroboration where we are using a hindered reagent, bulky reagent, so that we make sure that addition of boron to less substitute carbon is favored. That steric factor favors addition of boron to less hindered carbon of the triple bond. Now, in case of hydroboration oxidation of a triple bond, carbonyl compounds are obtained. If carbonyl compound, carbon-oxygen double bond, has hydrogen attached to carbonyl-carbon, that's an aldehyde. If on that carbonyl carbon both substituents are carbons, that's a ketone. So hydroboration oxidation gives aldehydes. Hydroboration oxidation of terminal alkynes gives aldehydes. So A is going to give aldehyde as a product. And so we're considering these four. This one, A, is aldehyde as a product. That's correct. B, this one is actually reaction intermediate and it's a wrong intermediate. So that's not correct. C, that's ketone as a product. That's not correct. And D, that's also aldehyde. So A and D give correct products for transformation A, for reaction A. Then the question is which one is correct for reaction B? And B is oxymercuration demercuration. Oxymercuration demercuration proceeds according to Markovnikov rule, where oxygen adds to more substrate carbon of the triple bond and hydrogen to less substrate. And now products are methyl ketones. And B is methyl ketone. This one is actually intermediate. This is vinyl alcohol. Vinyl alcohols are unstable and they rearrange to carbonyl compounds. So these vinyl alcohols, this is vinyl alcohol. Vinyl, double bond, and alcohol. Vinyl alcohol. So all of them are unstable and they rearrange to corresponding carbonyl compounds. So correct answer is A. And finally, question 6. What is the product of the following reaction? So here we have an alkyne. This one is an internal alkyne. We had internal alkynes before. We had one similar question. Actually, it was, I think, question 4. Yeah, this was also internal alkyne. So variation on the question 4. So what is the product here? Where we have a reaction of alkyne with deuterium in the presence of palladium and pyridine. A very similar reaction. It's again Lindlar catalyst, and again same type of reaction. Addition of hydrogen that is syn from the same side of double bond. The reason why I gave you this one is just to show you how reaction conditions could be a little bit different, and and variations of this transformation. First, instead of using hydrogen, we are using deuterium, isotope of hydrogen. So you have to show that in the reaction product. That product is not protium, it's deuterium. So in a line formula, we don't show hydrogens. So this is CH3, we are not showing these 3 hydrogens, and CH3 and CH and CH3. But if it's hydrogen isotope deuterium or tritium, we have to show that. So you will show deuterium or tritium. So if on the test this was possible, let's say one of the 4 choices, this was a possible choice, and you had another one with this same compound, but deuterium atoms were omitted, you just had a line formula, that would not be correct. This one is correct. And finally, palladium, we can use palladium, let's say, as a powder. We don't have to absorb it on carbon or some other inert support. We can use it as a powder. It's just a little bit more expensive, but it's reusable. Simply after the reaction, we filter it out. It's still a metal palladium in powder, put it back in a bottle, dry it, put it back in a bottle, and it's ready to be used next time. So this is variation. It doesn't have to be palladium on carbon. Just the palladium is actually what reacts. Whether palladium is on something or not doesn't matter. And finally, PY is abbreviation for pyridine. This general abbreviation for pyridine. So I wanted to make sure that you see that we don't have to provide formula of pyridine. That would be 6-membered aromatic ring with nitrogen. We don't have to write it pyridine. We can simply use this abbreviation PY. We can type it as abbreviation PY. And again, since addition is syn, product is cis-alkene. Okay, so that completes exercises related to chapter 10. And at this point, I'm going to end recording.